Thank you very much. It's my pleasure to be here. So Brilliant Blunders. Let me get straight to it. Why did I write this book? For many reasons. I'll just give you a few. One is that I wanted to correct a certain idea of how people think that science is actually done, and I'll come back to that towards the end. I also wanted it to be comforting to the rest of us to know that even some of the real luminaries have made some serious blunders. While I was writing this book, every time somebody would ask me, what is your book about? I would say it's about blunders and it's not an autobiography. So I have chosen, out of the 5 people that that I'm discussing in the book, I will try to talk briefly about 3 of them tonight. Let me just say that the people were chosen such that the theme of evolution connects all 5 of them, and by that I mean evolution of life on Earth, evolution of the Earth itself, evolution of stars, and evolution of the universe as a whole. So this theme kind of runs through all the people here. So let me start with the first one. The first thing you notice about life on Earth is its enormous diversity. It's enough to go outside here, and you will see many, many plants, many insects, birds, people walking their dogs and whatnot and so on. Nobody actually even knows how many species there are on Earth. The latest serious estimates put it at maybe 8.7 million, but estimates actually range all the way from 5 to about 100 million. And the reason it's very uncertain is that, it's enough to take a teaspoon from under your feet, and that contains already thousands and thousands of species and so on. The second amazing thing about life on Earth is the enormous degree of adaptation and symbiosis. Symbiosis is this scratch my back and I'll scratch yours type of a relationship. If you look at the bee has precisely the size that it fits into the flowers on which it feeds, and then the pollen gets on its body and it transfers this to other plants and so on and so for other flowers. This particular fish here, this clownfish, lives among the poisonous tentacles of this sea anemone, and the fish protects the anemone protects the fish. The fish has on its body this special mucus that protects it from the poison of its host and so on. So these were 2 things that were known to naturalists for centuries, that there is an incredible diversity of life on Earth and that life is extraordinarily adapted. Everything is this symbiosis. And there was no good theory for all this life on Earth, and until a certain person came, and it's this person, what you see him when he's old, Charles Darwin. And in one book, which he published in 1859, on the origin of species by means of natural selection, he really changed all the ideas that were before him about how life evolved and developed on Earth. By the way, when I write books, I like to go to the places where people worked. So in this particular case, I was happy to be there and actually hold the first copy of this book in my hand, and so on. It's a great feeling. I put this plot here of evolution not because it's correct, because it isn't, but only because it's very pretty from a graphics design perspective. I have one of my daughters is an artist and also studied graphics design, so I decided I'll put this here. The reason I say it's not correct is that it gives you the impression that, let's say, things here are more evolved than things there, and that's not how it works. You see, evolution is not a ladder. It's more like a bush. Things evolve in different directions. And things that are equidistant from the starting point are all basically equally evolved. Darwin didn't like to draw genealogy trees. He never published one, actually. But in his notebooks, he did them occasionally because it helped him to think. And this is one that he drew in one of his notebooks, although he never published. I like this one because he has primates down here and the man up there. So he was thinking about it, but he never published it. Okay, what is this theory that Darwin came up with? The theory has 4 pillars, and those pillars are all supported by one grand mechanism. Now, this drawing here has nothing to do with Darwin's theory of evolution, but the reason I put it there, it actually comes from a Hindu myth, because you see it has 4 pillars, and they're all supported by one grand mechanism. So it fits what I want to say. There is, by the way, a story about Bertrand Russell, which is almost certainly not true. But, you know, there is a proverb in Italian, si non è vero è ben trovato, which says, even if it's not true, you know, it's a good story. So I'll tell you this story, and that is that once Bertrand Russell gave a talk, and he showed this kind of drawing, and some woman in the audience asked him, and on what does that giant turtle stand? And he said, on another giant turtle. And she insisted, and on what does that turtle stand? She said, yet another giant turtle. But she continued, and on what does that stand? And at that point he said, lady, I'm afraid from there it's turtles all the way down. So it's probably never happened, but it's a good story. Now, what are these 4 pillars? So first there is the pillar of evolution itself. Namely, species are not immutable. The species that we see today, they have evolved. It's not the species that were once. In fact, most of the species that were on Earth have become extinct, and we just see the things that evolved from them. Second, there is gradualism. Namely, things happen very slowly. Darwin learned this from his geologist friends. In the same way that the surface of the Earth, you know, is continuously eroded and so on and evolves, this is what happens. Namely, you're not going to watch a species and see it turn into another species. It takes tens and hundreds of thousands of generations for that to happen. Then there is common descent. Common descent says all the species that you see now on Earth, all 8.7 million, actually started with one species at the beginning. This is why we do here, you know, today, we do experiments in origin of life, because we think it all started, you know, from chemistry, went to some biology and so on. And finally, there is speciation, which says, well, if it all started from one, how come there are so many? Well, Darwin says, and he drew this in his notebook again, there is this branching. You know, I mean, a certain species splits into 2, then another that splits into 2, that splits. And since at every time you double the number of species, very quickly you are going to get to very large numbers. I like this page very, very much, because look what he wrote at the top. He wrote, I think. You see, he was very humble at that stage, and, you know, he just presented this as an assumption. Now, as I said, all of this was supported by one grand mechanism. And that mechanism is natural selection. There is a philosopher, he still lives, Daniel Dennett at Tufts, and he wrote once that he thought that natural selection is the greatest idea anybody has ever thought of in any field. This may be a bit of an exaggeration, but it is an incredible idea. And the amazing thing about this is that it is so simple once it's pointed out to you. And the idea is the following. It says like this: suppose I have a certain species, and suppose that certain members of this species have a certain characteristic that gives them a certain advantage. For example, that they survive better, and also that they have more offspring. And imagine now that that characteristic is also inheritable. Then, Darwin says, what's going to happen is over time, the whole population is going to shift towards that characteristic. Very simple, right? So that's the idea. Now, let's see some examples of this. So, in England, there was this peppered moth with light colors, which originally it was camouflaged so well that, look, you can barely even see it here on this tree here. There it is. But then, this was in the 19th century. In 1848, there was the Industrial Revolution. They started pouring enormous amount of soot into the atmosphere, which blackened all the trees. At that point, this light-colored peppered moth became, you know, it's sticking out like a sore thumb. It became the target of massive predation. And became almost completely extinct. At the same time, the melanic or dark version of this started thriving because it was then camouflaged very well. Now, they actually adopted somewhat greener practices in 19th century England at that point, and this light-colored peppered moth actually was saved from total extinction. These snakes are all red snakes, which, depending on where they lived, they adapted and evolved to have the colors of their surroundings. Where do we see today actually most natural selection working? With bacteria. Bacteria, because the populations are humongous and also they multiply very, very fast, the entire evolution process for them is actually compressed. So you can see that. So I'm sure many of you heard of MRSA, for example. There are these bacteria that are resistant to many, many antibiotics. Actually, every year in the US, there are about 14,000 people who die from bacteria that are resistant to all antibiotics. And this is a very serious problem because they don't discover many antibiotics. Until last year, a new one was not discovered for about 15 years. So it's a serious problem that we have to deal with. Now, everything I told you is great. Darwin had this theory that explains everything about life on Earth. So where is his blunder? Well, here it is. Now, Darwin didn't know any genetics, and that in itself is not a blunder, because nobody knew genetics at the time. So we cannot blame him for that. The theory of genetics that existed was that of blending heredity, which meant the characteristics of the mother and the father get mixed in the offspring in the same way as you would mix paints. That was the idea. And Darwin adopted that because that was the prevailing theory. This is not a blunder, as I say, because he didn't know any better. That's what the theory that existed. His blunder was in not recognizing that if this were the correct theory of heredity, natural selection could never have worked at all. And let me try to explain that very briefly. Imagine that you have a population of 1 million butterflies, and they are all white. And there is one butterfly that is black. And imagine that black gives you an advantage. In Darwin's theory of evolution by means of natural selection, this would have meant that over many, many generations, the whole population should turn black, basically, because that's the one that gives advantage. What would have happened under blending heredity? The black butterfly would mate with a white butterfly. They would produce a gray butterfly. Black is gone. That's it. The gray butterfly now will mate with another white butterfly. It will produce a paler shade of gray, and so on and so on. Not only the population would not turn black, you would not see black again. That's it. So this Darwin at first didn't catch. It was pointed out to him by an engineer. It's very appropriate. We are at School of Engineering here. Fleming Jenkins, who actually noticed this and wrote about this. Now, I will say, Darwin didn't catch that, but he was unhappy with blending heredity even before Fleming Jenkins told him about this. Here I just explained, what I just told you that how it works. How does it really work in nature? It works because it's not blending like paints. It's more like shuffling of cards. If you have a jack, and having a jack is good, it doesn't matter how much you shuffle, you are left with a jack. That's what genes do. And this was told by Gregor Mendel, who did these experiments with peas, green peas, yellow peas, and so on. The way it works is that you get from one parent this, which is capital A, which is black, let's say, the other one, which is white. Together they give gray, but the capital A and the lowercase a stay. They don't disappear because they don't blend. So then you get from one parent again A and A and A, and depending on how those mix, you could get black, gray, or white. And if black gives you an advantage, eventually it will all turn black. That was the idea. Now, I noted that Darwin thought about this, and he wrote a few amazing things. This is 1857, even before he published On the Origin of Species. He wrote that he thought that it will turn out that heredity is more like mixing, like cards, and not like fusion, like paints. And then in 1866, he wrote something which was truly amazing, because the reason it was amazing is that How come all of those who thought about blending heredity didn't think about this? Darwin said, wait a second. Every woman produces a distinct male and a distinct female, and not some intermediate hermaphrodite. You know, and so he noticed that there was something wrong with blending heredity. He just didn't know how to correct it, because Darwin, if there was one thing he was really weak in, is mathematics. So to do calculations with statistics and so on, the type of thing that Mendel did, he couldn't do. So he couldn't do that. Now, there is an interesting story about this, because there are 4 books that claim that when Darwin made statements like this, it was because he read about Mendel's experiments and not because he thought about it himself. Mendel's paper was published in 1865. Now, so I became a bit obsessed in trying to determine whether or not Darwin could have known about Mendel's experiment or not. And somebody from the Darwin Project, Andrew Sclater, even checked some of that even before me. So together we managed to solve that. So basically, let me tell you, when Darwin died, Mendel's paper was not in his possession. Mendel's paper was published in an obscure journal of the Brünn Academy of Sciences. That's the same as Brno today. But he wasn't subscribed to that, and he never read that. But there were 2 books in Darwin's possession that mentioned Mendel's experiments. One of them mentioned in a few lines, you couldn't understand from that anything, you know, what Mendel actually did. The other book was by this gentleman here, Wilhelm Olbers-Focke. I actually, again, held this book. This was Darwin's copy. You see, he wrote his name there. So it's true that he had this book where Mendel's paper was mentioned. But you know where it was mentioned? It was mentioned here, in those pages that were never cut. Darwin never read this book. And let me tell you, even had he read it, he would not have been much illuminated, because Focke did not understand anything about the meaning of Mendel's experiments. So he didn't know about this. Let me go to the second scientist. This is Linus Pauling, the greatest chemist for sure of his generation, the only person to ever have gotten 2 Nobel Prizes without sharing them with anybody. 2 Nobel Prizes by himself. One was for peace, but one was for chemistry. Here he is with his model for certain proteins. He became older, but the model stayed the same because it was a correct model. So what happened with this model of proteins? In 1948, Pauling decided, he tried to determine the structure of some proteins, and he somehow convinced himself that the carbon and nitrogen and the 4 atoms around them having the structure have to be in one plane. And then he wanted to somehow twist the whole structure while keeping those things in a plane. You cannot see it here on the projector, but he actually tried to fold the paper to make it to make it look like that. And indeed, he came up with this kind of structure, which he called the alpha helix. And this was a beautiful structure that he came up with. Now, at that time, people started to do Xray diffraction experiments. These are experiments where you want to determine the structure of a molecule, you shine X-rays on it, and from the way the X-rays are scattered, you determine the structure. Now, Pauling actually attacked it from the other way. He first used chemistry, structural chemistry, to determine the structure, and then only tested it by X-ray diffraction. Okay? So he did this for this molecule. He was very happy with it, but there was one thing that nagged him, which was the distance between these 2 turns in his model was 5.4 angstroms. An angstrom is 100 millionth of a centimeter. And the X-ray diffraction showed a certain feature at 5.1 angstroms. Now you can say, 5.4, 5.1, what's the big deal? The difference is good enough for government work. But he was unhappy with this. He was very unhappy with this, and he actually did not publish his model for 13 years. because he tested every little bit. He asked the assistant to do X-ray diffraction on small pieces of this and so on, tried to twist the model, things and so on. After 13 years, he convinced himself that it has to be right and published it. It turned out to be the correct model. Actually, the reason for this turned out to be an artifact. I mean, there is a coil inside the coil, and they produce an artifact at 5.1 angstroms. So he was right. Then he turned his attention to DNA. DNA is arguably the most important molecule there is. And he noted two things. Well, one thing he knew and the other he noted. You see, DNA is supposed to be responsible for replication, right? I mean, that's the molecule that replicates itself. So in 1948, he suggested the following. He said, look, for something to be able to replicate itself, it is easiest if it is composed of two parts that precisely complement each other. Because if that is the case, then if I have half the molecule, I can determine the full molecule because it's exactly the complementing of that. So he noted that, and this tends to point towards a structure that is composed of two parts. There was also something known as the Chargaff rules after chemist Erwin Chargaff. You see, DNA is composed of sugars, phosphates, and 4 bases, which are called A, T, C, and G. Well, they have more complicated names, but we'll call them A, T, C, and G. And Chargaff noted that every piece of DNA you take, the number of A's is equal to the number of T's, and C is the number of G's. So that also kind of argues for a two-part thing. And yet, when Pauling finally came up with a model for DNA, his model had 3 spirals in it. How do you do complementary with 3 spirals? The bases were outside, the phosphates were in the middle. The phosphates all have a negative electric charge. It was a disaster. So here it was.
This is Linus Pauling's failed attempt to predict the structure of DNA. The problem with his triple helix model is that the phosphates form the helical core, with the bases pointing outwards. This would be impossible under normal cellular conditions. Each phosphate group is negatively charged, and so many negative charges forced together would repel each other, literally driving the structure apart.
So basically, Pauling's model was like this. It had 3 strands, not 2. It had all the negative phosphates in the middle, which would have really repelled each other, because similar charges repel each other, so it would have driven the structure apart. And it did not obey the basic rules of chemistry, because he wanted to keep the structure together by some hydrogen bonds, by hydrogen atoms connecting things together. But you know, you may have heard that DNA is called a nucleic acid. An acid is something that when you put it in water, it releases hydrogen. But if hydrogen is supposed to hold the structure together, how can it release the hydrogen? So basically, his model was wrong on every level. And this was the greatest chemist of the world doing this. So what happened? Now, do you know for how long he thought about this model? He thought about the alpha helix for 13 years. For how long do you think he thought about his model for DNA? For 1 month. So one of the things I've done in this book is try to get into the heads of these people and to understand why they made the blunders they made. Now, I'm not a psychologist, so it's not very easy for me to do. And even if I were, I mean, these people are dead, so I cannot ask them any questions. But I did talk to all the people who are still alive and worked with Pauling. So there are a number of questions. Why the rush? Why he published it in 1 month? Why the forgetfulness? He completely forgot about his own rule of complementarity, about the Chargaff rules, all of that, and so on. And what about basic chemistry, that it wasn't an acid? So let me just give you a flavor of why I think all of these things happen, just to show you that even these greatest of scientists are human after all. Why the rush? He was very competitive. And he knew that both the group in Cambridge with Lawrence Bragg and the group in London, which he didn't know about Watson and Crick, he barely heard about them. But Lawrence Bragg was there in Cambridge, and so were Watson and Crick, but he didn't know much about them. And Maurice Wilkins was in London. He knew that both of them had better X-ray diffraction images than he had, and he wanted to come in first. What about, why did he forget the Chargaff rules? I don't really know, because he certainly knew about this, but I have a hunch. He just couldn't stand Erwin Chargaff. He was once on a boat with Erwin Chargaff going from the US to Europe, and Chargaff was a very intense individual, and Pauling was a rather laid-back individual. And Chargaff kept nagging him about his rules and things, and I almost think that Pauling took out of his head anything that Chargaff ever said. And finally, what about the basic rules of chemistry? I believe that Pauling fell victim to his own previous success. Basically, what he learned from the story of the alpha helix was that his original hunch was correct. And he spent 13 years testing and testing, but all of that turned out to be details. And he felt that his basic idea of the model is correct. It's not that he didn't know that, this is not an acid and so on, but he thought those are details which will work themselves out later. So I think that's what happened. Now, of course, the correct model came from Watson and Crick. The bases are on the inside. A connects with T, C connects with G, which exactly explains why the Chargaff rules happen. It is exactly according to Pauling's original idea of complementarity, so all of that works fantastic. It has only two strands. What did they do once they found the model? What any two young people, Jim Watson was in his 20s, would do. They went to the local pub. And this is the Eagles pub in Cambridge, where at that point, at lunch, Francis Crick stood up and said, "We discovered the secret of life." And they have a plaque there to do that. And, it's a wonderful pub for many reasons. RAF pilots wrote their names on the ceiling there at World War II and so on. I strongly recommend to go there for other reasons than just this plaque. Anyhow, I showed you Pauling when he was younger and older. I'm going to show you them also when they were older. Since then, Francis Crick, unfortunately, has passed away. Jim Watson is still very much alive. I want to show you this picture because I actually knew about certain statistics that the dean here described. This is a meeting on proteins that Pauling organized in the 1950s, and I want you to take a look at that picture and tell me what it is that you see that is strange. There is only one woman, Beatrice Magdoff from the Brooklyn Polytechnic. Today in proteins meetings, it's about 50-50. This picture also happens to be amazing because of the large number of Nobel laureates in this image. Here is Pauling himself. This is John Kendrew, who got the Nobel Prize. Maurice Wilkins got the Nobel Prize. Max Perutz got the Nobel Prize. Lawrence Bragg. There is Francis Crick, got the Nobel Prize. Jim Watson, and so on. Lots of Nobel Prizes in this thing. There is one small thing that I'll just mention. I mean, I'm wearing a tie now because this is a distinguished lecture, but when I go to scientific meetings, I don't wear ties anymore, and nobody does. Here, everybody wears ties. My last person is Albert Einstein. I like this photo of him best because when my hair is a bit longer, it looks like that. But this is where the similarity ends. I like to say sometimes that Newton is dead, Einstein is dead, and I also don't feel so well. Now, Einstein, of course, did something pretty amazing in his theory of general relativity. Now, some of you may be a bit rusty on your general relativity, so I will just explain to you in a couple of sentences what this is all about. Forget for a moment about this term and, forget about the fact that this is an equation. I'm just going to tell you what it is. So this thing here describes all the mass and energy that is in the universe. That's this. This thing is the strength of gravity. And this thing describes the geometry of the universe. So the geometry of the universe is determined by the mass and energy of the universe. That's what it says. And that's what also determines gravity. In other words, what Einstein says in general relativity is the following. You have imagine that there is a trampoline, and I'm standing on the trampoline. Then the trampoline sags. And then, if I throw some balls onto this trampoline, they will somehow move in the shortest paths in this curved space. So Einstein says, basically, that gravity is not some mysterious force that acts across distance. It is really just the fact that masses cause space to warp. And then once space warps, that's the force of gravity. That's what causes masses to move in a certain way. That is the idea in Einstein's theory. Now, once he suggested this theory, he realized that there is a problem with it. And that is, you see, he thought that everything in the universe is static. Nothing moves. But then think about this for a second. If everything, gravity means that everything attracts everything else. If everything attracts everything else, how can it be static? This thing would just collapse. So what he did, he added this term here, which is called the cosmological constant, which said that at every point there is a repulsive force that precisely balances the attractive force of gravity, so that everything is in equilibrium. Now, as it turns out, it was not a good idea anyhow, because while you could make things in equilibrium, it was an unstable equilibrium. Like me trying to balance this thing here, the slightest deviation will cause it to fall. But he thought he was happy with this, because he thought everything is static. But then, these two gentlemen here, Edwin Hubble, after whom our telescope is named, and this Georges Lemaitre, discovered that actually our universe is expanding. It's not static. And then Einstein said, if everything is expanding, I don't need to balance everything at every point, because all that gravity is going to do now is it will just slow down the expansion. Like, I throw my keys up, the gravity of the Earth slows them down. That's it. It doesn't need to be in equilibrium precisely. So he regretted having put that term in, and he took it out of his equation. Took it out. Then, however, in 1998, not that long ago, two groups of astronomers discovered that the expansion of our universe is not slowing down, it's speeding up, it's accelerating. And you know what appears to be pushing it to accelerate? That term that Einstein took out of his equations. So his mistake was not to put that term in. His mistake was to take it out. Had he left it in, he might have predicted that our universe should be accelerating. So, some people are just so smart that even when they think they made a mistake, it's actually brilliant. So, I want now to come back to the question of why I really wrote this book, other than everything that I just told you. You see, very often we're told that progress in science, and actually not just in science, in every creative enterprise, is a direct march from A to B. And in fact, nothing can be further from the truth. Progress in science and in any creative enterprise is more like this. There are lots of false starts, of blind alleys. Many times you need to go back to the place from which you started. That's how progress is actually being achieved. Now, here is the thing. We teach many of our students, we evaluate many proposals and processes and so on by not allowing people to make mistakes. Now, I want now to be very careful in what I say. I do not advocate any mistakes that come out of being sloppy, out of haste, or out of being inexperienced. All of those are inexcusable. However, we also want to be able to think outside the box. And guess what? When you think outside the box, you may make a blunder. But occasionally, you will get a breakthrough. Those are the things I call brilliant blunders. Okay? So, and we can introduce this also into evaluation processes, and I'll give you an example. For about 10 years, when we allocated time on the Hubble Space Telescope, we reserved about 10% of the time to give it to proposals deemed risky. And by that we meant proposals that appeared very thoughtful, but which you couldn't be sure whether they can really reach the objective that they did. But if they did, there was a potential for great reward. Okay? So those are the things I would like to encourage in all of our thinking. Thinking outside the mainstream. Not all the time, not 100% of the time, but allowing for unconventional thinking that can lead to, you know, once in a while you will get the new Facebook. I don't know what, something, yes? I mean, I will be the first to admit that if somebody told me that one of the greatest inventions in recent years would have been a software tool that allows you to send 140 characters to somebody, I would have thought these people are completely crazy. And yet, right now, we are in a situation where entire revolutions in countries were driven by this tool, you know? So you never know. You should allow for this possibility of breakthroughs and for serendipity, too. You know that in the medical profession in particular, more than half of the medications they found are found serendipitously. They are looking for a medication for tuberculosis, and they actually find that it works on depression. That's how it works. So basically, that is my main message here. So I would like scientific blunders, and in particular, these things I call brilliant blunders, which are true for any creative process, can actually be the portals for discovery. Thank you very much.
We have a Q&A, so invite you.
Yeah, I'll be happy to try to answer a few questions if there are. Don't be shy. You must have some questions. Yes. No, she can, yeah. As long as I hear it. So I actually look, I mean, most progress in science is achieved incrementally. And there is a lot to be said for that. You cannot, you know, devote everything to this outside-the-box thinking, because much of that outside-the-box thinking will lead to blunders. I mean, the place where we see this best, actually, and I have somebody who accompanies me here now who's starting a new company, is in the startup business. You know, 4 years later, more than half of startups fail for various reasons, you know, and so on. But every now and then, they lead to something really great. So that industry adopted a model where, you know, you take big risks and you try to this. In normal processes, I think you should allow for a certain fraction of the time or of the funding or the whatever for that kind of thing. And I don't think you should devote all you think to it. but the main thing I want to say is don't tell people that making a mistake is horrible. The previous director of IBM used to say this. You know, he said, we should not punish anybody who made a mistake because they thought boldly in the company's advantage. Okay? Any other questions? Yes? Have I made any brilliant blunders? Not of the level of the brilliant blunders that these people did, because I don't come nearly to the brilliance that they exhibit. You know, I thought about this a little bit. So once, for example, I had a situation where an astronomer, I'm an astrophysicist, so an astronomer claimed that the central star of certain objects we call planetary nebulae, suddenly it was a she. She claimed that it's not one star but two stars, a binary system. And she claimed that about 6 such planetary nebulae. And before that, nobody has known of any such object that had 2 things. Now, I was fascinated by that and developed the whole theory of how you form these objects with binary stars and so on. While I was developing that theory, other astronomers observed those 6 objects that she observed and found that none of them really has a binary star in it. I mean, these were all mistakes on her part. Now, on my part, it was not a mistake. I had a brilliant theory, only there was nothing to explain with it because the object did not exist. Well, later it turned out that while those 6 objects did not have binary stars in them, many others did, actually, that were discovered. And my theory turned out to be very good at the end. But originally I thought, look, I devoted all this time to develop a theory for something that doesn't actually exist. Yes?
Do you think our society is based on thinking outside of the box there in Silicon Valley?
No, I don't think our society is based on thinking outside the box. I think that even at Silicon Valley and so on, I think there is perhaps a greater appreciation of thinking outside the box. But I still think that, you know, much of the work we do for very good reasons is actually incremental. You know, you build on what you know. You build on things that you know will give results, you know, and so on. There is a lot to be said for that. It's just that sometimes you may miss a potential for a big breakthrough if you completely disallow this thinking outside the box. Yes?
What do you think of Linus Pauling's advocacy of taking megadose of vitamin C?
Yeah,
Do you think should have stopped with the area of expertise?
So, yeah, Linus Pauling, you know, late in life, you know, became a big advocate of vitamin C, which he thought, you know, will cure everything, more or less. Cancer, everything, and so on. Now, I do not discuss that, even though I mentioned it in the book, I don't discuss. You see, every one of my luminaries made more than one mistake in their life, and I decided consciously not to make this a laundry list of all the mistakes that they made, but chose to concentrate just on one blunder for each scientist. In Pauling's case, I believe that that was a manifestation of something that actually we see happen very frequently, unfortunately, with great people. You see, suppose I'm a great scientist. I made some incredible discovery. Then I may find it hard to go back to the mundane day-to-day work and so on. And very often, late in life, some of these people, they want to make something new that is big. So they go into areas in which actually they don't know that much about, thinking that they are going to make a big discovery there as well. But it's hard, and they don't make it. So I see that as part of that kind of manifestation. Yeah?
You had said that mistakes and laziness and inexperience are inexcusable. Don't you see a mistake in
Yeah, mistakes in inexperience are a way to gain experience. But when I said that sentence, what I meant by that is that I would not consider that as a brilliant blunder, in the sense that, you know, if people don't recognize that they are inexperienced, then that's not excusable. Yes, I mean, if they recognize they are inexperienced, but they, you know, they still think that maybe they have something, I don't know what, that's one thing. But if they are inexperienced and not recognize that, that's inexcusable. Any other? How are we time-wise? Are we okay? Okay. Yes. Here is one more. Yeah. Please. Yes. Okay, so the first, he asked for my opinion on the Cosmos show and so on. So actually, Neil deGrasse Tyson is a personal friend of mine, so of course I will not say anything bad about his program. But I happen to think that it's a very good program, and of course it's oriented towards not people like me, but towards the general public, and I think it achieves a very good way, because people who maybe normally would not have watched science programs watch it as a result of this. You see, one of the key problems that we have in society is, on one hand, there is the problem of teaching science to our children, but on the other, there is the problem that we have many, many adults who did not have a good scientific education, and many of those people are actually in position to make decisions, important decisions, and if they are scientifically illiterate, that's not a good situation. Now, concerning about things that we cannot experience with our senses, and he mentioned in particular the Oort cloud. There's a cloud of like comets that surrounds the solar system. There are many things we cannot experience with our senses. I mean, we do not see atoms with our eyes. We certainly don't see quarks, which are, you know, the constituents of protons. In fact, we have a theory which says that we cannot see a free quark. But this doesn't prevent us from believing in them, because those theories make enough predictions that we can test and see if the theory, you know, agrees with that or not. So the whole trick of a scientific theory, and what distinguishes a scientific theory from other systems of belief, is that scientific theory works according to the scientific method, which says, you see certain phenomena. You propose a theory that is supposed to explain everything that you have already seen, and it is supposed to be able to make predictions for experiments or observations that you have not yet done. And if those new experiments or observations do not agree with the theory, you reject the theory, not the new observations and the things. That is the thing. So these two things, it must be consistent with all facts and must be able to make predictions about new experiments. And that is where other types of systems completely fail. Okay.
Wow. Well, on behalf of us all, I'm sure everybody in the room has exactly the same sentiments. This was a phenomenal talk. I learned a lot. I'm a little overwhelmed at this moment, but thank you so much.